Put simply, this project would not exist without the ASME's Electric Human Powered Vehicle competition. Therefore, our vehicle's goals have always been structured around the competition guidelines and handbook. Our team's personal goals in selecting this project closely align with ASME's goals in creating this event. We both value sustainability, and we both understand that there exists an inherent inefficiency in the transportation industry with medium distance travel. What that means is that most people's daily commutes are short enough that an entire gas-powered vehicle is often overkill, yet long enough that a bike ride is impractical and just plain exhausting. The ideal vehicle in the eHPVC would perfectly fill this gap. More personally, another one of our team's main objectives was coordinating a long-term project with so many moving parts. Our team prioritized equally dividing up the labor as much as possible, which helped keep our workload fair and relatively light throughout the 2 semesters. We also decided against team roles for specific aspects of the vehicle and instead opted to rotate what each team member worked on. This meant that each team member learned about and worked on every single aspect of the vehicle at least once, and if we needed help with anything, we always consulted each other. This made the project feel more coordinated and interactive, and it just helped us get to know each other more. It's a lot easier to put in your best effort when you feel like your team has your back.
For the design of our vehicle, we first strive to understand what the different technologies that go into making various types of HPVs are. Much of that research was performed by searching the internet for reliable sources that explain various aspects of bikes. For instance, one article may talk about drivetrains and the different types there are. A video may explain the pros and cons of different frame configurations. Or a textbook might explain how different types of tires can affect cornering. The research phase goes beyond just finding out existing technologies. Textbooks and communication with the engineers from Cartwright, our sponsor, identify optimal geometric parameters that will enhance the performance of the vehicle. An example of these parameters can be the angle of the driver's seat that is best for power transfer, and how the caster angle between the spindle and the tire patch will impact steering performance. Once the team has a solid understanding of the technologies and physical principles behind human-powered vehicles, we then began conceptual selection. The basis of this part of the design process is to subdivide the potential vehicle into separate subassemblies, and then each subassembly into 4 or 5 configurations. These configurations are ranked within matrices, and all the best configurations from all subassemblies are collected to make a total or complete conceptual design. The process of turning the conceptual design into a final design requires applying the physical principles the team learned from Cartwright, textbooks, and other sources. Dimensions such as angles and lengths are defined, models are created, and analyses are done. And these analyses are either computational or done by hand with mathematical models learned from textbooks and other sources. After each analysis, the design of the vehicle is iterated upon to better meet design requirements. The guidance from Cartwright also helps with improving the design and drive it to a final version that is ready for competition.
In the design of the Trike's roll protection system, or RPS, finite element analysis played a critical role in ensuring the strike's structural integrity and ensuring that it met competition requirements. Our goal was to keep the max stresses below 290 megapascals, which was the yield strength of the aluminum alloy, preventing permanent deformation in both the 2670 Newton top load case and the 1330 Newton side load case the competition mandates. Initially, our FEA showed a 156 megapascal maximum stress for the top load and 210 megapascals for the side load. This was on the low end of our 1.3 to 1.5 factor of safety that the team was shooting for. Digging deeper, these higher than expected maximum stresses were due to the mesh quality of our simulation and not due to the design of the roll protection system. This was found when the mesh quality values were seen to be 0.005 on a scale of 0 to 1. To ensure that our FEA was giving us accurate test results, we contacted our advisor and he recommended that we convert our 3D pipes to 2D elements to lower the amount of work the computer has to do in the simulation. Additionally, quad meshes were enforced, which better fit the cylindrical pipes of our trike. These techniques vastly improved our mesh quality, with most of our elements surpassing 0.88 mesh quality and a maximum skewness of only 0.67, indicating that the members were matching up correctly. With this new high fidelity mesh, our refined FEA showed maximum RPS stresses reduced to 131 megapascals for the top load and just 100 megapascals for the side load, providing factor of safeties over 2 compared to the aluminum's 290 megapascal yield stress.
Once the design of our trike was finalized, it was time to move on to manufacturing. Manufacturing the trike was by far the most intense part of our process. Our sponsor Catrike was a huge help in having us translate our design from the CAD software to the real world. This process began with tube bending. Catrike has several types of mandrel benders at their disposal to bend a few different diameters of aluminum tubing. These benders had to be programmed to bend the tubing to spec for our frame. Once we got all the tubes bent, we began the process of notching our tubes to fit together for welding. Most of the notches could be done on Catrike's universal notching jig, but for some of the more unique geometries, we had to create 2D sketches of the notch and apply it to the tubes, and then cut those tubes using a Dremel. After the tubes were notched, we had to design and build our welding jig. Our jig was constructed from 80/20 aluminum extrusion, and it was designed in such a way that each part of the frame was securely located and optimized recycling 80/20 that we had in storage to reduce our costs. After constructing the jig, it had to be adjusted to fit our bent tubes. From then, we had our frame welded, heat treated, and then powder coated. Once the frame was complete, we finished assembling the rest of the trike with parts that we ordered.
So for the physical testing for our bike, the competition had a few requirements. For starters, we had to test and ensure our trike could stop at a speed of 25 kilometers an hour in a distance of 6 meters or less. We then tested to ensure our trike could turn within an 8-meter radius and demonstrated stability by driving 30 meters at an average speed of 5 kilometers an hour in a straight line. After the driving tests were completed, we then finished the remaining safety tests, such as ensuring the emergency stop button for our electric assist worked. Finally, we confirmed our FEA through physical tests by testing the roll cage with our tallest rider strapped into the vehicle to ensure that the RPS didn't fracture and that the rider was unharmed and did not touch the ground, while the vehicle was on its side and completely flipped over. We also made sure each rider logged at least 30 minutes minimum riding the vehicle to prepare for the competition and to meet the competition's requirements.
Since this project is associated with ASME's Electrical Human Powered Vehicle competition, the team has not only been developing this vehicle for the final project of our undergraduate curriculum, but to also compete against other universities' ASME chapters. The competition has been a year-long process that involves 4 major events: a design report, a design presentation, and 2 races that will be happening at Liberty University. The first race is a head-to-head style drag race, where teams compete against each other, and the team that wins the race moves on to the next race in the tournament. And the second race is a 2-hour-long endurance race, where the team will be racing around a predetermined track and will have to dodge certain obstacles and compete against and do certain challenges during the race.
We learned a lot over the course of this project. Our best learning experience from this project is being able to see the entire engineering design process and project management progression from start to finish. This will be very beneficial for us for our future careers. For future improvements for the bike, if our team had had more time and budget, we would have liked to explore different fairing options, whether it be designing and manufacturing a fairing ourselves, or just looking at the market and seeing what other fairing styles could benefit our bike. Thank you so much for watching this video on our project, and we hope you consider us for the Senior Design Showcase.